Hi and welcome to the second video on moments from the Year 2 Mechanics course, and in this video we're going to take a quick look at what happens when the forces are not perpendicular, as you can see from the title there, and then we will bring it all together in the final video. But in this one we're just going to have a look at what happens in this particular case when the forces aren't perpendicular, because up till now all we've done is dealt with forces going straight up or down, left or right. We haven't had to deal with things on an angle. So here we go. That's what we know, that our moment, our turning force, is force times by the distance, and d is the perpendicular distance from the point to the line of the force. Now if the line of the force is, as we've seen previously, going straight up or down, then the perpendicular distance just becomes the distance from the point to where the force is being applied, sorry, the pivot to where the point is being applied, and that we've seen that in all the previous examples we saw in previous videos. However, if we've got a force doing that, so we've got a force here that's at an angle, and let's say we're going to consider the moment about the pivot, which is point P here, then we need to know the perpendicular distance from the point to the line of the force, which is going to be that distance there. And as you can see from the right angle triangle that we've now got, we've got a right angle triangle here, where this one here is the hypotenuse, this is going to be the opposite side, so therefore that distance there is going to be d sine theta. So what we get is our moment is the force times by the perpendicular distance, which is d sine theta. Okay, so let's just have a look at a quick example. So what we've got is a light uniform rod. We've got a pivot at point P here. We've got some distances. We've got and a couple of forces at angles. So let's have a look at what's going on with these forces. Right, so let's take clockwise to begin with. So the clockwise moment is going to come from this 8 Newton force here. So what we need to do is have a look at what is the perpendicular distance from the line of the force to point P. So let's just put that in. That's going to be that distance there, which is 5 sine 70. So our clockwise moment is going to be 8, the force times by the distance, 5 sine 70. So that's 37.6 Newton meters. If we now have a look at this one, well, it's slightly up because like the force, it almost feels like it's going away from the pivot. But the key thing there is, in fact, it's the moment we've set up here to the line of the force. And the line of the force, if we just extend that back down this way, we can now see clearly we've got our perpendicular distance there. That's our purple line. This angle here being 40, so our perpendicular distance to the line of the force is actually 3 sine 40. So what we've got is 12 newtons times by 3 sine 40, 33.8 newton meters. And so we've got a resultant moment in the clockwise direction, so this thing will rotate in about P in that direction. Okay, so that's the concept. Let's have a look at a kind of exam style question. So we've got a uniform rod, AB, it's got mass, it's got length, and it's being held against a rough vertical wall. Key idea being that it's rough, so therefore we've got some friction going on there. And you can see from the diagram, that's all explained there. If you want to take a moment to read through, that's fine. We've got tension in the string being dB, is 25 over 4. That's all that. So we've got to show two results. First, we've got to show that x is 3a, so the distance to our point C here, where we've got a particle of mass 3m being attached. We've got to show that that distance there is 3a. And we've also got to show that the horizontal component of the force exerted by the wall and the rod has magnitude 5 mg. Right, so let's start off and stick some force on. So there's our 3m mass, and so that's got a weight of 3 mg. We've also got the mass of our uniform rod, so that's acted through the centre of the rod, so we've got another 3 mg there. And then we've got tension in the string, 25 over 4 mg. And then the other forces that we've got are the forces where it meets the wall. So I mentioned before we've got friction, stopping it slipping down the wall, so friction is going to be acting upwards. And then we've got the reaction force of the wall against the rod, so I'm going to put that one. So we've got friction there and reaction force there. So there's our forces. Now let's do a little bit of kind of preliminary work and figure out what's going on here to begin with. We are going to need that angle in there, so let's see what we can do with that. Well, we know we've got a triangle. There's ADB. We know the distance 3a there, 4a there. Bit of Pythagoras gives us BD is going to be 5a, so a 3, 4, 5 triangle. And from that, we've got sine theta is going to be 3 over 5. And also the other thing I'm going to need is that perpendicular distance from B to A, because what I'm going to do in a second is take some moments about A. So I need the perpendicular distance from the pivot to the line of this force here, because this is our force that's not perpendicular. So let's have a look down here. What we've got is, if we consider now this right angle triangle here, where we've got 4A is the hypotenuse, so therefore that red dashed line there is going to be 4A sine theta. Right, so on we go, and the first thing I'm going to do is prove that the distance from the wall to our mass, which is hanging at C, is 3A. So let's take some moments about A, because we don't know anything about the forces here, and also by taking moments about A it kind of takes out those two values and simplifies things a little bit. So let's have a think about what's going on at A. Let's start off with our clockwise moments. So that's going to come from the mass of the rod and our mass that's hanging at point C. So we've got 3mg times by x, that's that one there. And then we've got 3mg times by 2a, middle of the rod. So that's why that's times by 2a, our force times distance. And going anti-clockwise, we've got our force here, 25 over 4 mg, times by the perpendicular distance, the line of the force, 4a sine theta. Now what I'm going to do now is a whole bunch of tidying up on this side here, as well as a bit of dividing through by mg. So let's get rid of the mg's. There we go. Let's replace the sine theta with its value, which is 3/5. And now we can see we can do a bit of simplifying there. We can do some cancelling with the 4's. That's all okay. And I think that's pretty much all of that done. So now on this side here, I've got 3x plus 3 times 2a. So I've got 3x plus 6a. And on this side here, what have I got? I've got 15a. So there we go. All of a sudden, that's now looking a whole lot more simple. We are looking to prove that x equals 3a. And that's a simple enough job. Move the 6a over, divide by the 3. And there you go. X equals 3a as required. Right, that's part A done. Let's go on and have a bash at part B. The horizontal component of the force exerted by the wall on the rod has a magnitude of 5 mg. That's the result we're going to try and show. And if we're talking about a horizontal force here, well, it makes sense in this case to resolve the forces horizontally as per normal. So let's see what we got going to the right. Well, we've just got R, okay, that's right. And then the force going in the opposite direction. The only thing that's going to come is the horizontal component of this one, which is going to be 25 over 4 cos theta. And if sine theta is 3/5, we can see from the triangle up here, cos theta is going to be 4/5. So there we go. Let's put that in. And there we go. We can see we can do a bit of cancelling with the 4's, a bit of dividing by the 5's. And there we go. We've got R equals 5 mg. Okay. So that example was there just to illustrate what's happening with the non-perpendicular forces. You're going to spend most of your time dealing with things like kind of ladders leaning up against walls and this kind of stuff, but I'm going to put that into the next video. This video is just about establishing those principles.